Mars has long been viewed as humanity's next frontier, but making it a habitable environment presents a monumental challenge. Though the red planet holds potential, the technologies required to get us there and sustain a colony are still in development. In this expanded presentation, we'll discuss not only the challenges, but also the technologies needed for Mars colonization, including their current status and projected timelines for availability. Technological challenges. Transportation to Mars. Technology needed. Interplanetary Transport Systems, ITS. Description. To establish a colony, we need a reliable way to send both humans and large amounts of cargo to Mars. Current spacecraft are designed for short-term missions, but interplanetary travel requires more robust, reusable vehicles capable of carrying large payloads, habitats, and life support systems. Current status. SpaceX's Starship. Currently the most promising option for large-scale missions to Mars, Starship is designed to carry up to 100 passengers with cargo in a fully reusable system. The spacecraft is undergoing extensive testing with several successful suborbital launches. NASA's Artemis program. While primarily focused on the Moon, the technology developed in Artemis, particularly the Space Launch System, SLS, and Orion spacecraft, may serve as stepping stones for future Mars missions. Estimated availability. SpaceX aims for an uncrewed mission to Mars by the late 2020s and a crewed mission sometime in the 2030s. NASA is currently focusing on the Moon, with a crewed Mars mission projected for the late 2030s or early 2040s. Technology needed. Mars entry, descent, and landing DL. Description. Landing large payloads on Mars is incredibly difficult due to its thin atmosphere. Current EDL systems like parachutes and retropropulsion need to be adapted for larger spacecraft and heavier loads. Current status. NASA's Perseverance rover successfully landed using a combination of a heat shield, parachute, and a sky crane. However, this system can't support the weight of human habitats. SpaceX's Starship uses retropropulsion, firing rockets to slow descent, and is designed to land on Mars' surface using the ship's own engines. Estimated availability. SpaceX's Starship may demonstrate Mars landing capabilities in test missions by the late 2020s. More advanced systems for larger structures and habitats will need further development, creating a livable environment on Mars. Technology needed. Habitat construction. Description. Mars colonists will need pressurized habitats with controlled climates, life support systems, and protection from cosmic radiation. Inflatable habitats, 3D printed structures using Martian soil, and underground bunkers are all potential solutions. Current status. NASA's Habitat Challenge. NASA has been running contests to design sustainable habitats for Mars. The winners propose 3D printed habitats made from local materials regolith to minimize transported resources. Big's Mars Habitat. Architectural firm Big Jarkingles Group has proposed concepts for domes made from locally sourced ice, which would provide radiation protection. Estimated availability. Early habitat prototypes could be ready for deployment in the 2030s, but a fully self-sustaining settlement will likely take several decades to perfect. Technology needed. Life support systems. Description. Life support systems will need to manage air, water, and temperature inside habitats. This involves recycling oxygen, removing CO2, and ensuring access to clean water. Current status. ISS technology. The International Space Station, ISS, has life support systems that recycle air and water, but these systems need to be adapted for the Martian environment and made more efficient. NASA's MOXIE experiment. Aboard the Perseverance rover, the MOXIE device has successfully produced oxygen from the Martian atmosphere by splitting CO2. Scaling this up would be critical for air production and rocket fuel. Estimated availability. Improved life support systems may be tested on the ISS within the next 5 to 10 years, while scalable versions like MOXIE for Mars could be operational by the mid-2030s. Resource utilization and sustainability. Technology needed. In situ resource utilization, ISRU. Description. Since transporting materials from Earth is cost prohibitive, Mars colonists must harness local resources to produce essentials like oxygen, water, fuel, and building materials. Current status: water extraction. NASA's upcoming Mars Ice Mapper mission will locate subsurface ice deposits. Water can be extracted from this ice or from hydrated minerals. Oxygen production. MOXIE has demonstrated the potential to convert Mars CO2 into oxygen. The next step will involve building larger, industrial-scale systems. Fuel production. Using a chemical process known as the Sabatier reaction, Mars CO2 and hydrogen from water can be used to create methane fuel, which SpaceX plans to use for return trips to Earth. Estimated availability. ISU technologies like water extraction and oxygen production systems could be tested in the 2030s, with full-scale implementations needed for permanent settlements by the 2040s. Technology needed: agriculture and food production. Description: colonists will need sustainable food sources, as resupply missions from Earth would be limited. Farming on Mars will require innovative techniques like hydroponics, aeroponics, and potentially genetically modified plants adapted to Martian conditions. Current status: space farming. NASA has been growing plants on the ISS to study how they react to microgravity and low-light environments. Experiments on growing food in simulated Martian soil have shown promising, though limited, results. Hydroponics and aeroponics. These soil-less farming methods are advancing on Earth and could be adapted for Mars. They use less water, and plants grow faster in controlled environments. Estimated availability: space-grown crops could be feasible by the late 2030s. Scaling up food production for a large colony would require additional time, likely into the 2040s. Physiological challenges. Technology needed: health solutions for low gravity. Description: Mars gravity is only 38% of Earth's, which could lead to long-term health problems like muscle atrophy, bone density loss, and cardiovascular issues. Exercise regimens, pharmaceutical solutions, or even artificial gravity habitats may be necessary to counteract these effects. Current status: ISS studies. Astronauts aboard the ISS exercise for several hours daily to combat the effects of microgravity, but the lower gravity of Mars may require less intensive measures. Artificial gravity, using centrifugal force, is still in early theoretical stages. Estimated availability: pharmaceutical countermeasures and specialized exercise protocols could be in place by the 2030s. Artificial gravity habitats are more speculative and may take several decades to develop. Technology needed: radiation protection. Description: Mars lacks a magnetic field, exposing colonists to harmful cosmic rays and solar radiation. Habitats and spacesuits will need advanced shielding to protect residents from radiation-related health risks. Current status: regolith shielding. Some concepts involve building habitats underground or covering them with Martian regolith to shield against radiation. NASA is also testing new materials, like hydrogen-rich plastics, that could block radiation effectively. Water shielding. Water can be used as a protective barrier against radiation, and systems that combine water storage with shielding could serve a dual purpose. Estimated availability: early shielding solutions like regolith-based habitats could be ready by the 2030s. More advanced materials may be developed over the next 2 decades. Psychological challenges. Technology needed: solutions for isolation and mental health. Description: living in small, isolated environments on Mars could lead to psychological stress, loneliness, and mental health issues. Colonists will need tools to manage stress, and communities will need systems for conflict resolution and mental health care. Current status: HICs and Antarctic research stations. Simulated Mars habitats, such as HICs in Hawaii, are studying the psychological effects of isolation. Research from similar environments, like Antarctic bases, is providing insights into how humans cope with isolation. Telepresence and VR. Virtual reality (VR). Environments may help reduce feelings of isolation by simulating Earth-like experiences or connecting colonists with loved ones on Earth. Estimated availability: VR systems and telepresence tools are already available and will likely play a key role in Mars missions in the 2030s. Advanced psychological support systems may continue to evolve throughout the century. Economic and political challenges. Technology needed. Cost reduction and commercial space access. Description: reducing the cost of getting to Mars is critical for sustainable colonization. This involves reusability in rockets, ISRU technologies, and the development of a space-based economy. Current status: reusability. SpaceX's Falcon 9, already having a successful track record, has already dramatically reduced launch costs by reusing rockets. The fully reusable Starship by SpaceX, in advanced testing phase with several prototypes undergoing test flights, aims to revolutionize space travel by reducing costs even further, potentially bringing down the price of interplanetary travel. Beyond rockets, a sustainable colony will require the establishment of industries on Mars to minimize dependence on Earth. Private sector involvement. Companies like Blue Origin, Rocket Lab, and Relativity Space are also working on technologies aimed at reducing the cost of space access. This growing commercial space sector is making space travel more competitive and cost-effective. Estimated availability. Fully reusable launch systems like Starship could be ready for Mars missions by the late 2020s or early 2030s. The development of a Martian economy and industrial base, such as mining for materials or manufacturing products in space, will likely emerge in the latter half of the century. Technology needed. Governance systems for Mars. Description: establishing a sustainable colony on Mars will raise complex political and ethical questions. Who governs Mars? What legal rights do colonists have? How are resources managed? And how do we prevent conflicts over limited resources? We will need new legal frameworks and governance models for a Mars colony. Current status. Outer Space Treaty, 1967 currently. Space law is governed by the Outer Space Treaty, which prevents any nation from claiming sovereignty over celestial bodies, including Mars. However, the treaty doesn't address the complexities of governance for a permanent human settlement. Space law developments. The rise of private space companies has spurred discussions about the need for new laws regarding resource extraction, property rights, and governance in space. NASA's Artemis Accords propose a cooperative framework for lunar exploration, which could be expanded for Mars. Estimated availability. New space governance frameworks will need to be in place before the establishment of permanent colonies, likely in the 2030s or 2040s. International collaboration will be key, with the involvement of organizations like the United Nations and spacefaring nations. Future technologies that could accelerate colonization. While current technologies are being developed to tackle the challenges of Mars colonization, future innovations could drastically change the timeline and feasibility of establishing a permanent presence on the Red Planet. Some of these speculative technologies include nuclear fusion for energy and propulsion. Description: nuclear fusion, the process that powers stars, could provide nearly limitless energy for Mars colonies. In space travel, fusion propulsion could dramatically reduce travel time to Mars, making trips safer and faster. Current status. While nuclear fusion remains theoretical for now, several private companies and research institutions are making progress. The International Thermonuclear Experimental Reactor, ITER, in France is one of the most ambitious fusion projects, aiming to demonstrate that fusion can produce more energy than it consumes. Estimated availability. Fusion power for Mars colonies is decades away, with optimistic estimates placing it at mid-century. For now, nuclear fission reactors, such as NASA's Kilo Power project, will likely serve as a reliable energy source for early colonies. Artificial intelligence and automation. Description: AI and robotics will play a crucial role in establishing and maintaining Mars colonies. Robots could be used for construction, resource extraction, and habitat maintenance, reducing the need for human labor. AI systems could optimize resource management, automate agriculture, and manage life support systems. Current status. NASA's Robinaut and Perseverance's Ingenuity helicopter are early examples of robots assisting in space exploration. AI is already being used for mission planning and control in space missions. Autonomous construction. Companies like Icon are developing 3D printing technology that could be used to build Martian habitats. AI systems could help operate these machines autonomously in harsh conditions. Estimated availability. Advanced AI and robotics will likely be integral to the first human missions in the 2030s and could be fully automated for construction and maintenance by the 2040s. Synthetic biology. Description. Synthetic biology involves modifying organisms to better suit life on Mars. This could include genetically engineering plants to grow in Martian soil or engineering bacteria to produce oxygen, water, or food from Martian resources. Current status. Research in synthetic biology is advancing rapidly. CRISPR gene editing technology has made it possible to modify organisms with greater precision. Experiments on Earth have already shown that certain bacteria can survive in extreme conditions similar to those on Mars. Estimated availability. While early applications like genetically modified crops may be possible in the 2030s, more advanced uses of synthetic biology, such as creating custom organisms to produce vital resources, may be ready by the 2040s or 2050s. Quantum communications. Description. One of the major challenges of a Mars colony will be communication delays. Quantum communication, which uses the principles of quantum entanglement, could theoretically enable instantaneous communication across vast distances. Current status. Quantum communication is still in the experimental phase, with early tests demonstrating quantum entanglement over short distances. The technology is currently too immature to be applied to space communication. Estimated availability. Quantum communication might become a practical technology later in the 21st century. In the meantime, colonists will rely on more conventional methods like relay satellites, which would still involve significant communication delays, up to 22 minutes. The dream of colonizing Mars is closer than ever, but it requires significant advances in a wide range of technologies. From interplanetary transportation to life support systems, sustainable agriculture, radiation protection, and governance frameworks, every aspect of life on Mars will rely on innovation. While some of these technologies, such as reusable rockets and ISRU systems, are already in development and may be available within a decade, others, like fusion energy and quantum communication, remain distant prospects. However, if the current pace of technological development continues, we may see the first human footsteps on Mars within the next 2 decades, followed by the gradual expansion of Martian outposts into self-sustaining colonies. This journey will be one of the greatest challenges in human history, but it will also open new doors for exploration, discovery, and the survival of humanity beyond Earth. In summary, the path to Mars will likely unfold in stages. 2020s. Development of reusable rockets, Starship, initial uncrewed missions, and ISRU technologies. 2030s. First human missions, early habitats, and resource utilization systems. 2040s to 2050s. Expansion of Martian settlements, fully operational ISRU, advanced farming, and health solutions. Beyond, large-scale terraforming, synthetic biology, and the development of a Martian society. The colonization of Mars, while fraught with challenges, is no longer just science fiction. It's a future that we are actively building step by